Thanks for the introduction. I'm excited to tell you about bandwidth hard functions. This is joint work with Ling Ren and Samson Zhou. Ling was at MIT when he did the work, and Samson was at Purdue. Samson has now started as a postdoc at IU. To motivate bandwidth hard functions, let's look at the problem of password hashing, right? So you have a user like myself who creates a account, and this account stores some hash of my password, hopefully some salted hash. Now, oftentimes hackers can break into the server, steal the hash value, and mount a fully automated brute force attack. Right, so here the attacker will just check every password guess in some large dictionary. So he'll, check the hash of password. He'll check the hash of, some variation of password. Keep going, and eventually he'll crack my password. By the way, my password is not actually 123456. Though I imagine right now, if one was monitoring the PlayStation authentication server, this might look like this. Okay, so offline attacks are a common problem, and in the last few years, we've seen large-scale breaches at many organizations. These breaches have affected actually billions of user accounts. So to defend against offline attacks, what we desire is a moderately hard function. So informally, what we want is a function that can be computed reasonably quickly on a standard personal computer, but somehow it should be prohibitively expensive for an attacker to try millions or billions of guesses to evaluate this function. And this should hold even if the attacker has customized hardware to compute this function. So even if the attacker has an application-specific integrated circuit, we still want to make sure that it's prohibitively expensive for the attacker to brute force the user's password. So why is it such a big deal if the attacker can build an ASIC? ASICs are powerful, right? So here's one of the Bitcoin miners, these machines are reasonably inexpensive, a couple $1,000s to buy one of these ANT miners, and they can, they're measured in terahashes per second. So these devices can try, trillions of hashes per second, and in particular, they are many orders of magnitude more efficient than your CPU on your personal computer. So, right, if you wanted to do a comparable amount of work on your personal computer, you're going to need buy a lot of processing units, and this is going to be expensive. So, really, what we want to ensure is that the dollar cost, measured in amortized cost per evaluation of the function, should be prohibitively expensive for the attacker. And there's really two key sources of cost here. There's capital cost, the cost to actually buy the equipment, and there's the cost of actually running the equipment, which is largely dominated by electricity. So how do we reduce the advantage of an ASIC? Over here on the left, we've got our ANT miner, and at least the capital cost is fairly cheap, at least if you amortize by the number of instances it can compute per second. And similarly, the energy cost per evaluation of the function is also, marginally, just marginal. Whereas, the cost to buy a CPU and to power the CPU is significantly more expensive. So to make this function more egalitarian, we'd like to make this function somehow memory hard, which means that cost should be dominated by memory-related cost. So that can either be the cost of purchasing a bunch of DRAM chips to evaluate the function, or the cost of powering those DRAM chips. So again, capital costs and electricity costs. So memory hardness really focuses on designing functions that have high area time complexity, which means that your capital cost will be high, right? You need to buy a lot of DRAM chips to be able to evaluate this function. And bandwidth hardness, the topic of the paper today, focuses instead on the second factor, right? What's the cost of actually running this equipment? Okay, so memory hardness has a lot of work, right? Percival in 2009 suggested that if you want to decrease a parallel attacker's advantage, one natural way to do this is to increase the size of the circuit that computes this function. So intuitively, our goal here is to force the attacker to lock up large amounts of memory for the entire duration of computation. So ideally here, if we're running in time n, we can hope to force the attacker to lock up n blocks of memory for n time steps. And there's lots of work on constructing memory hard functions. Various definitions of memory hard functions. Percival had a definition. Allwin and Serbanenko improved the definition in 2015. There was the password hashing competition, where we had lots of contestants, and Argon 2 was declared the winner of this password hashing competition. Allwin and Serbanenko proved a Pebbling reduction that shows that if you want to analyze the security of a data-independent memory hard function, actually all you have to do is focus on a nice little pebbling game in the graph, and you can ignore everything else. There have been attacks on data-independent memory hard functions. There's a security proof for scrypt. Scrypt is a data-dependent memory hard function. So this was actually Best Paper Award at Eurocrypt in 2017. And then there are, a recent line of work developing improved constructions of data-independent memory hard functions. So there's a tremendous amount of work on memory hardness. But by contrast, bandwidth hardness, this second factor, has been largely ignored. So Ren and Davidus, they published a paper at TCC last year kind of pointing out that, while there's all this work on memory hardness, the energy cost has really been ignored. So in particular, just because you force the attacker to use a lot of memory doesn't necessarily mean that the attacker has to consume a lot of energy. After all, a DRAM chip, doesn't consume much energy unless you're actually transferring a lot of data into and out of that DRAM chip. So they proposed that a natural goal would be to ensure that any attacker is kind of forced to transfer the maximum number of blocks between cache and memory. And in fact, we can relax this a little bit. So either the attacker has to transfer the maximum amount of words between cache and memory, or the attacker has to do a super linear amount of work. So this is the goal of bandwidth hardness. And in contrast to memory hardness, there are many open problems in this area. So before I define bandwidth hardness, let me first distinguish between a data-dependent and a data-independent memory hard function. So a memory hard function, the intuition is that computation cost should be dominated by memory-related cost. Scrypt, of course, is one of the original constructions of a memory hard function. But scrypt is data-dependent, which means that the memory access pattern depends on the user input. In this case, the user input is typically a password, and so it's pretty sensitive. And you don't want to be leaking that information via a side channel. So in the password hashing competition, there was a lot of focus on developing data-independent memory hard functions, where basically we're just going to require that the memory access pattern doesn't depend on the sensitive user input. And this eliminates most side channel attacks that one might think of. So how does one specify a data-independent function? Well, typically the way one specifies a function is in terms of a graph labeling problem. So we start off with a hash function h, which in analysis, h is typically viewed as a random oracle. And we start off with a directed acyclic graph, G, which encodes data dependencies. And then we just have labeling rules. So the label of the first node, 1 here, is the hash of the input. The label of an intermediate node is the hash of all of the parents of that node, and the output of the function is just the label of the last node. Right, so given a graph G and a hash function H, I can just specify a function FGH, by labeling this graph. So then if I want to talk about evaluating a data-independent memory hard function, I can use the language of graph pebbling. Now, if I'm looking at memory hardness, typically I use something called the parallel black pebbling game. But when I talk about bandwidth hardness, we're trying to reason about data being transferred to and from cache. So in this case, the red-blue pebbling game turns out to be more appropriate. So here, a pebbling is just a sequence of states where BI denotes the set of data labels that are stored in memory at time I, and RI denotes the set of labels that are stored in cache at time I. So the only difference between red-blue pebbling and black pebbling is that in black pebbling, one doesn't distinguish between whether a pebble is stored in cache or in memory. Now, of course, the goal of this game is to eventually place a red pebble in the last node, right? So we want to compute this function, which means that we eventually have to place a pebble on the last label. So, of course, there are some rules that govern what you can and can't do in a legal pebbling game. Legal pebbling moves. One legal pebbling move is, we'll call it a blue move. So you can change the color of a pebble. And this corresponds to transferring a data label from cache to memory, or vice versa, transferring that label from memory back to cache. And then there's also a red move, and a red move is actually computing a new label. And here the only constraint is that before we can place a new red pebble on a node, we have to have red pebbles on all of the parents of that node. Why is this? Well, before you can compute a new data label, you have to have all of the dependent data labels already stored in cache so they're available to the processor. And finally, one is allowed to discard pebbles at any time in this game. Okay, once we've defined the rules of red-blue pebbling, how do we define the cost of a red-blue pebbling? So in a red-blue pebbling, we have two types of moves. We have red moves and blue moves. Blue moves correspond to transferring a value to and from cache, right? So this is the expensive step, even on an application-specific integrated circuit, right? So we have two parameters, CB and CR. CB denotes the cost of a blue move, the cost of transferring one data label to or from cache, and CR denotes the cost of computation, computing a new label, which is just the cost of querying your hash function one time. So then the pebbling cost of a graph G, given a cache size M, is just the minimum of the red-blue pebbling cost, where we are going to minimize over all legal red-blue pebblings. Okay, good. So if we want a secure, bandwidth hard function, one would like to find a graph G with maximum red-blue pebbling cost. Now, unfortunately, there's an inequality in the world, right? And the inequality is that the attacker gets to play this game, but he gets to play this game with advantageous constants, right? So the attacker's cost for a red move is actually significantly cheaper than the honest party's cost for a red move. Well, the attacker's cost for a blue move is comparable to the honest party's cost for a blue move. So we've got blue moves, which are egalitarian. They cost, roughly the same for the attacker or the honest party. And then we have red moves, which, there's a tremendous difference between the cost of a red move on an ASIC, where you've, built the SHA-256 hash function into your circuit, versus the cost of computing this function on your computer. Right. So the attacker gets to play with advantageous constants, and unfortunately, life's not fair. We have to find a way to cope. So, what this guy here is pondering is, how can we make sure that the function is energy intensive for the attacker as well, even if the attacker gets to play with advantageous constants? So the definition then of bandwidth hardness that Wren and Desiderata proposed is that we just want to make sure that this ratio between the attacker's cost and the honest party's cost is constant, right? So the attacker shouldn't be able to dramatically improve his cost by building an ASIC. Right, the top here, it's red-blue cost for the honest party. The bottom is red-blue cost for the ASIC, and we want them to be comparable. So one sufficient condition here is just to make sure that the cost is dominated by the cost of blue moves, right? So if the cost of pebbling this graph is at least the cost of n blue moves, then the honest party can find a pebbling with cost n times CB, and it will cost the attacker the same amount, and we'll achieve our goal of egalitarian computation. Okay, so with that said, let me briefly mention a couple of candidate memory hard functions. So Argon 2, of course, was the winner of the password hashing competition. And Argon 2 has a data-independent mode, Argon 2i, which was originally recommended for password hashing. They now recommend Argon 2ID for reasons I'm not going to get into right now. One of the reasons Argon 2ID is recommended actually is because of a series of black pebbling attacks that was developed on Argon 2I, which reduces the amortized area time cost. So it reduces your capital cost. We're not sure about your energy cost, but this attack at least reduces your capital cost. So then there's Catena, another password hashing contestant, which receives special recognition. DR sample, which is a proposal at last year's CCS that, at least in an asymptotic sense, gives you optimal amortized area time cost, and another construction called AAT sample, which was from the same paper and also gives you asymptotically optimal area time cost, though with better constants in the provable lower bound. Okay, so what we know which iMHFs are memory hard, but which iMHFs are actually maximally bandwidth hard. So prior results, Wren and Desiderata showed that the Catena bit reversal graph and the balloon hashing function developed at Stanford are both actually maximally memory hard, given appropriate assumptions on the size of the attacker's cache. They also showed that scrypt, this data-dependent memory hard function, is also maximally bandwidth hard, though their proof only applies to a limited class of attackers. So what are our results? We show that Argon 2i, DR sample, and AAT sample are all maximally bandwidth hard. So in particular, Argon 2i is an important function to analyze here because it's the winner of the password hashing competition. It's already been deployed in libsodium. And it doesn't have optimal area time complexity, but as we're showing, if you care about just energy cost, it actually does give you optimal bandwidth hardness. We also show that any function with high cumulative memory complexity must also have reasonably high energy cost. So this is at least a nice result to know, right? So it's not like building a memory hard function and a bandwidth hard function are necessarily conflicting goals. Actually, to build a bandwidth hard function, oftentimes one way to do it is to make sure that that function actually is memory hard. This also implies a S-crypt lower bound. The lower bound we get is slightly weaker than the lower bound of Wren and Desiderata, but it's an unconditional lower bound, so it applies for any attacker in the PROM model. This is some of the results that are known. Another major open question in Wren and Desiderata's paper was whether or not there's a pebbling reduction. So in the black pebbling world, where we're thinking about memory hardness, Allwin and Serbanenko proved an important theorem, which basically said that, in the random oracle model, any attacker evaluating our data-independent memory hard function can be described by a parallel black pebbling strategy with comparable area time cost. And this theorem is tremendously important because it means that lower bounds that you prove in the black pebbling game generalize to any attacker in the parallel random oracle model. So in particular, if you want to prove security for your data-independent memory hard function now, you can just focus on the black pebbling game. So that's valuable. One might ask, is there a similar reduction for the red-blue pebbling game, right? So far, all of the bounds that Wren and Desiderata have proved and that we've proved, they are just pebbling lower bounds. But one might ask, does a pebbling lower bound imply a lower bound for any attacker in the random oracle model? Do lower bounds in the red-blue pebbling game actually imply anything interesting in the parallel random oracle model? I'll spoil my thunder. The answer is yes. But before I can tell you that, let me first define energy complexity. Right. So before I've defined red-blue pebbling cost, and this definition will look pretty similar, but I want to stress that this is actually a different definition than the definition of red-blue pebbling cost. Right. So what's the energy cost of an algorithm? Well, we're going to give our algorithm or attacker a cache with size MW. So in other words, space to store M words of size W. And now the energy cost of an algorithm A on input X, it's CB times the number of bits transferred to and from cache divided by B. So we're just to normalize by number of words transferred to and from cache, plus CR times the number of evaluations of the random oracle. So the definition might look a little bit different, but now I want to stress that this is a definition for an arbitrary attacker, right? This is not just a definition for a pebbling strategy. Now we're talking about an arbitrary attacker in the random oracle model. So of course, as before, the attacker has an advantage. He gets to play with advantageous constants. So then the energy cost of a function, we're just going to minimize over all attackers that correctly compute that function using at most MW bits of cache. Full definition allows for attackers that are only correct, some of the time, but for now we'll ignore that. So now we're just going to minimize over, look at the optimal attacker that evaluates this function and look at his expected cost. So our pebbling reduction, we want to show that any attacker evaluating the function can be viewed as a red-blue pebbling strategy. So one direction of this reduction is easy, right? If I have a red-blue pebbling strategy, it's very easy to translate this strategy into an evaluation strategy in the random oracle model. The harder direction is showing that any algorithm in the random oracle model can also be described as a red-blue pebbling strategy. Here we need a pebbling reduction, and what we need to do is use an extractor argument. I'm running short on time. I won't have a chance to go into many of the details. I'll just mention briefly that one of the key definitions in the proof is to define the set query first, where given a time interval between T1 and T2, we're interested in the set of labels that appear as input to a random oracle query before they appear as the output of a random oracle query. And then we're going to partition our time intervals into intervals such that the size of the set query first is at least 3m in each interval. And then one can show that with high probability, the attacker has to transfer at least MW bits between cache and memory during each interval. And one can also find a legal red-blue pebbling in which you never have more than 8m red pebbles, and the number of blue moves during each interval is at most 4m. So this gives us an equivalence between the cost of a red-blue pebbling and the cost of an arbitrary attacker in the PROM model. Okay, so given that, we can prove some lower bounds on argon2i, dr sample, and AAT sample. So argon2i, we can show that it's maximally bandwidth hard as long as you assume that the cache has size at most n to the 2/3. Dr sample and AAT sample, we get similar results, except here the result continues to hold even if the cache size is quite a bit larger, right? So even if the cache size is n to the 1 minus epsilon, dr sample is still maximally bandwidth hard. Okay, so I'm gonna skip the argument. We have some new ideas for how to prove red-blue pebbling lower bounds. In the interest of time, I'm not going to say anything about it. So I'll just conclude. So moderately hard function should ideally be both memory hard in terms of amortized capital cost and bandwidth hard in terms of energy costs. Our pebbling reductions now show that the red-blue pebbling game actually models the energy cost of an iMHF. So if you want to analyze security, sufficient to look at red-blue pebbling. DR sample, argon2i, AAT sample are all bandwidth hard. Finding the optimal red-blue pebbling is NP hard. We show this in the full version of the paper. I highlight it here because if you remember back to the first session, NP hardness was perfectly correlated with having your paper accepted. So I suppose this is really the true reason why our paper was accepted, because we had the word NP hard in our abstract here. So with that, I will conclude and take any questions.
Hi, nice talk. I think this work is really cool, and I think it's like a nice conceptual approach to like build theory around like details of real systems. I was wondering though, there are settings now, and like you could imagine a world in the future where like electricity, because of some revolution in clean energy, has become essentially like too cheap to meter, as they say. So I mean, it's kind of speculative, but like, what do you think the role of such analyses and involve energy cost would be in a world where electricity is like it's like free, right?
Yeah, I mean, that's a great question. Obviously, if energy costs decrease, you have these two sources of cost. That means that, the energy cost kind of becomes a negligible portion of the cost, and you just need to focus on capital costs at that point. But yeah, I don't know. I mean, I guess Bitcoin miners, they all move to like Iceland, right, where there's geothermal energy. Right, so one could imagine password crackers similarly packing up and moving to countries like Iceland to reduce their energy costs.
So the cost of password cracking would be purely the upfront cost of buying the hardware, at least in this model.
Yeah, so it would be the cost of buying the hardware, probably amortized over the lifetime of that hardware. So you could assume that your DRAM chip lasts for 4 years under continuous usage, and then you can kind of calculate what you would expect your capital cost would be.
So is there, maybe we can take it offline, but it kind of sounds like you're hinting at a definition of cost, like a cost model that includes wear on the hardware itself. Is that something you've thought about?
Yeah, we've thought about it. And I mean, at this point, I mean, the best I can offer is kind of like back of the napkin type calculations. It would be really cool to have a more rigorous study of these costs, but we can talk about that offline.
Thanks.